Okay, so uh, Dr. Sanjeev, just wait for 2 3 minutes. I'm waiting for some others to join as it is festive season. So after that, I will start. Okay, so as no one joined, so uh, I am starting the lecture. So welcome all for this fifth week of compiler design problem solving session. So in today's lecture, I will just so in today's tutorial, I will just go through some of the problems which are discussed in week assignment of week 5, and also some of the questions which can be solved using the topics covered. So in week 5, the topics covered are basically LL1 grammars, then parser, and mostly the operator precedence parser. So I am first covering the slides which are shown in the lectures. Then we will go through some of the questions of previous year, and some of the other questions if we will get time. So this week there are not much content about problem solving, because there are the problems which are uh, very correlated and mostly based on just two concepts. First is LL1 parsing and then operator precedence. So in week 5, first there was the example of this LL1 parsing. So It is actually a recursive non-descent parser, uh, non-recursive descent parser, sorry. And so there was one example of this. So what we do for parsing through LLM parser, we are first given some productions. Using these prod rules, we first calculate first and follow of all the non-terminals, and based upon first and follow rules, we will just create some uh, input symbol and versus non-terminal table, uh, and then we will do some predictive parsing algorithm. We are given predict parsing table like this. Then uh, we are given the input string, and we are provided a stack. So we have to do top-down parsing. We will do some we will use some algorithm for predictive parsing. So we will have a stack. We will take a top of this, and then the input symbol. We will see both of this, and based upon this we will choose the production we have to apply. And when we will apply the production, uh, if x is there, then we will pop the stack and then advance the input pointer. And else, if x is a terminal, there will be error. If there is an error entry, we will provide error. If there is any entry which is having some production, then the output will be production, and we will pop the stack and push the stack in such a way that the last terminal will be on the top of stack, like this. So what we have done in this, we are given this input symbol table for ETF grammar. What we have done, we have provided this string id plus id into id. We attached dollar as a uh, end of string, and we have this stack. We are provided the input, and corresponding action we will write here. So first we are here with start symbol on stack. We will start with the start symbol on stack, and when the stack will get empty and input will having the end of string symbol, we will say it is done. So at first we are provided this input string id plus id into id. Now we will see the uh, symbol on top of stack. Now here is only E. So what we will do, we will see top of stack and the input symbol, which is ID, and based upon this input symbol and E, we will see the parsing table. So just see here. Um, oh, sorry. Oh, I'm not able to use it. Sorry. Okay, so okay, start. Now we will see this E, we will see this ID, and based upon this we will go to this parsing table, and we will uh, just uh, see the non-terminal and that input symbol in the parsing table, and based upon that we will parse the string. So there is E, and for ID, here is ID. So the production we can use it is this. So the production we will use is E derives T dash. So we will write action parse E derives T dash. Now we will put it on the top of stack. We will pop this E and push this T dash in a fashion that first we will push T. First there will be E dash, and then there will be T. So if there is an stack, we will put it like the last symbol will go on the bottom of a stack, and the first symbol after in the right hand side will on the top of stack. So here is t dash we have applied, and there is e dash t. Now we will again see the top of a stack and the input symbol in our input string, input buffer. Okay, so there is t, there is id. So what will happen? We will see this in parsing table again. We have t as a non-terminal and id as a terminal. What we have got? We have got this t provides ft dash. Now we will apply this parsing rule on this string. So what will happen? T will be popped out, and what we will push? We will put ft dash on top of stack. So now we had this e dash already. Now we will put this ft dash. So what will happen? T dash will be at top at uh, will be there, and f will be on top of a stack. So again we will do the same. F, then id. What we have got? F is here and id is here. What we will get? We will get f derives id. Okay, so we will use this rule. Now we will pop out this f, and we will push this id here. Now we will again see id and id both are same, so we will advance input, means we will pop out this uh, id, and we will means pass this id, so it is gone. Now we will take our pointer to the next one. Okay, so there is plus. Now top of the string, top of the means first of the starting of the input buffer is plus, and top of the stack is t dash, because id is actually popped out. Now we will see what will happen if there is t dash and then there is plus. So we have got this t dash derives e epsilon. Okay, so we have passed it. Epsilon means there is no string or end of string. Now what will happen? Uh, there will be nothing, and t dash will be actually popped out, and end of sorry, no string symbol. Yeah, Sarita, please tell. You can tell, or you can write on the chat. So now we have t dash derives epsilon. Now what will happen? There is epsilon is the empty string, so there will be nothing in this top of stack. There will be only e dash that will be on that is only remained in the stack. So that is also the top of stack now. So top of stack is e dash, and the symbol on the input buffer is plus. So what will happen? E dash and plus. So e dash and there is plus. So what will happen? We can use this one. Okay. So e dash derives plus te dash. So e dash derives advanced input means pop the elements. Uh, if advanced input means if you have got same uh, terminal on this stack and input, then you will pop out the stack, and you will pass this what is there in input buffer that time, and you will advance the pointer from that symbol to the next symbol. That is happened here. So id was here also and here also, so this id is actually popped out, this id is passed. Now our pointer what was pointing the input buffer will be advanced to this plus symbol. That is actually means by advanced input. Okay, so we are actually advancing, means we are moving our pointer to the next one, whether that symbol will be passed with this grammar or not. Clear? Okay, so we were here, we have e dash, then we have plus. So what we can use is e dash derives plus t e dash. Now how we will push it? We will push it in reverse way. First there will be e dash, then there will be t, then there will be plus, and this e dash will be popped out, and this will be pushed in the stack. So e dash will be on bottom of stack, plus will be on top of stack. Now again there is a condition, there is this plus and plus both are matched, so this plus will be passed. Now this is passed, this is actually popped out. Now what will happen, we will see again. We have t, we have id, again t and id, we have t dash ft dash, again that will happen, f, then t dash in reverse manner, and again we have f, then id, we will see the table, f derives id, we will parse using this rule. Now there is id here and id here, so both are id, we will pop out this, we will parse this id, and again we will advance our pointer to this uh, asterisk sign, or you can say multiplication sign. So next one, now we have t dash and asterisk sign on the input buffer. So we have t dash and the asterisk sign. So we can use this production. We have used it. Again we popped out this t and pushed this one. Now we have again this multiplication symbol here. We will advance the input, and again we have got f on the top of stack and id on the next input symbol. We will again use this f derives id, then again we have id and id, then again advanced input. So we are remained with t dash and dollar. Go to t dash, t dash is here, dollar is here. So what we have got, this one, t dash derives epsilon, so we will use this. Now we are remained with e dash and dollar. We have e dash and dollar, so we have e dash derives epsilon. Okay, so epsilon is actually no string there. So here is this nothing is in stack, and we have this dollar, means end of string symbol in input. So we are done with it. Okay, so what we can infer, that this string can actually be passed through, uh, successfully passed through this grammar using LL1 parser. Okay, so this was the example. Now let's try this one for but here is no sorry, next one. Okay, so now there is uh, earlier we have talked about this top down parsing. Now we have the uh, this bottom up parsing. So construct parse trees from an input string beginning at leaves and working towards the top. What we will do again, so like for example, there is id into id, so we will go to this id into id, then this id we will go reverse of rightmost derivation. Okay, so we will go reverse and rightmost derivation. So we will take this f derives id, then for this t derives f, this one, then it is done, we will go to this one. So ultimately what we make a point that we will go in bottom to top manner like this. Okay, so there are shift reduce parsers which actually do this. So the general idea is to shift some symbol on input to stack until a reduction can be applied. Reduction means you will use the production to reduce the symbols that is input the stack. So, and again at each reduction step, a specific substring matching the body of a production is replaced by non-terminal at the head of production. Then the key decision during bottom-up parsing are about when to reduce and about what to production to apply, and a reduction is reverse of a step in a derivation. So if there is f derives id, so id will derive f, means from id we will go to f. So the goal of bottom parser is to construct a derivation in reverse. So like here we have id into id, we will go to f derives id, then from here we will go to t derives id, sorry, t into id, then t into f, then it will be t, then it will be e, means to the starting symbol. Then there is handle pruning. So what actually handle is? Handle is a substring that matches the body of a production and whose reduction represents one step along the reverse of the rightmost derivation. Okay, so reverse of the rightmost derivation. So there is the right sentential form, that is id into id, then there is handle what we will reduce, and there is reducing production. So we are given id into id, we will take this id, and from this id we will go to f. We can use this production f derives id, so from id we will go to f. Now again we will go to this f, and we can derive t derives f, then again t derives id, sorry, f derives id, and likewise ultimately where we will land, we will go to this e, means the start symbol. So handle means we are given substring, and we will match the production body, and we will reduce that. Now in shift reduce parsing, what happens? A stack is used to hold grammar symbols, and handle always appear on the top of stack. Okay, so every time we will use top of stack for the reduction part. Then the initial configuration, we have a stack which is having nothing, only dollar, and input string there is w, then we have the end symbol, this dollar, and for acceptance configuration we will see on stack we should have s, means starting symbol, and in input there should be nothing. So next are some basic operations what are used in shift reduce parsing. So there are four. First is shift, where we will shift the input substring to the stack. Then there is reduce, means if some substring on top of stack is matching to any production, we will reduce using that production. Like there is f derives id, so id will be replaced by f on top of stack. Then there is accept. In accept, what happens if there is a starting symbol on top of stack and end symbol on input, then we will say it is accepted. Then there is error. So if anyhow the string will not get accepted, then we will show some error, or anything other happens. Just a second. example is same, id into id. We have stack, we have input, we have action. So in input we will write this, in stack we will provide this dollar symbol, then there is id into id, then preceded by this dollar symbol. Then we will see this id and we will shift it. We have shifted it. Now we will see top of stack whether we can reduce or not. So there is id on top of stack, we can reduce id using f derives id. So we will reduce id to f, again reduce it to t. Then we have t, then we can shift it. We have shifted asterisk on top of stack. Now we have non-terminal, we shifted this id. Now we can reduce this id. So f derives id can reduce it to f, and then t derives t into f can reduce the t, and then e derives t, we will get accept. So ultimately the work of this shift reduce parsers are to actually uh, take some kind of decisions whether to shift and whether to reduce. So that is the actual challenge. uh, so like handle will appear on top of stack, like here you can see stack, there is input alpha beta gamma, and there is yz. So we will go in bottom to top manner. So next, there may be conflicts that may arise when we are using shift reduce parsers. Why? Because due to some grammar or some properties of grammar, we can land in some state where we are not able to decide whether we have to shift or reduce, or that there may be happen that we should which rule we can use to reduce it. Okay, so like here we are given this grammar statement derives if very if xpr, then if expression, then statement, or then else statement, and then other. So what can happen when we will see this on stack? If expression, then statement, and we will see we have input as else, then we have two possibilities. Either we can reduce using this to this statement, or what we can do, we can take this statement, we can shift this else on top of stack and wait for this statement. So there will be conflict for the compiler whether to use the shift operation or to use this reduce operation. Okay, so for that uh, uh, we have this shift reduce conflict. uh, that kind of conflict we say it as shift reduce conflict. Now in case of reduce, say we are given some grammar, say a derives alpha and b derives alpha. So what may happen if compiler will see alpha anywhere, so which reduction it want to use, it should use, there will be conflict. Okay, so alpha can be any non-terminal, so both can be used. That is the problem of this conflict, reduce conflict. Which reduction rule, which production rules it can use for this reduction? Okay, like here it has provided this id. So from id it can go to statement also, from id it can go to expression also, if you see. So that was all for this LL1 parsing. Then shift reduce. Now there is bottom up parsing. So in bottom up parsing there is operator precedence parsing, and there are some LR parsing. So in operator precedence parsing we use operator grammar. So the grammar we are given should be the operator grammar, then only operator precedence parsing can happen. We can apply only those for solving some equations. So what are the rules? There are only two rules. First is there should be no epsilon transition. So there should be no epsilon in right hand side, and there should be no adjacent non-terminals. So if there is non-terminal in between these those non-terminal, there should be at least terminal. So for example, here is given OP is also a non-terminal and E is also a non-terminal. So this is actually not a not an operator grammar. So we can convert it. How? We can go to this. We can apply this OP to this E, and what we will get E plus E multiply E and ID. Then there are some operator precedence. So in operator precedence, if how we show it in the table, if A has higher precedence over B, then we can write A greater than B. If A has lower precedence over B, then A less than B. If they have uh, equal precedence, then equal sign, and this dot symbol. So these are some symbols we can use. We will use, and there are some points to note. We have ID has highest precedence, then dollar has lowest precedence, and if two operators have equal precedence, then we check for associativity of particular operator. Then we will create uh, some precedence table like this. So for associativity, you can see plus is left associative, then multiplication is also left associative, so the left. So for example, we are given this string W. We will apply this dollar both side, and then we will insert the precedence in between each of the symbol. Then we will use the basic principle for it, that is scan input string left to right and try to detect greater and put a pointer on its location. Then scan backward till reaching less symbol, then string between less and greater is our handle. Then we will replace that handle to of the respective production. Then until we will repeat it until we will get the start symbol. So the algorithm what we use, we will initialize a stack to the dollar, then there is a loop for till we get the success. So we have U to be the topmost terminal in the stack, V the next input symbol. If U is dollar and V is dollar, then we will return. If U is less than V, means the topmost terminal in the stack is less than the input symbol, or U is equal to V, then we will shift or advance the input pointer. Otherwise, if U is greater than V, then we will pop the topmost symbol and call it V from the stack until the top of stack is less than V. If anything rest happens with it, we will provide the error. Then if we are given this example, so for example, we are provided that previous string only, like this. So in this string, what we will do, we will we will have this stack, we will have this input symbol, then we will like previous one, we can write the actions or remark. Then we are provided this operator precedence table, based upon which we will take the decision about which operation we have to perform. Either we have to push or pop. So on top of stack there will be dollar, and in the input we will have this string preceded by this dollar. Now we will see the top of stack and the initial of this input. We have this dollar and there is id. Now going to this id and dollar, we will see the operator precedence table. We have id and we have dollar. So what we can see, id is having greater precedence to the dollar. So as it is having greater precedence, it will be pushed to this stack. Now we have id and plus, so we will see id and plus. Again here id is having greater precedence, so what we will do, we will pop out this id and plus will be there again. Now there is nothing, there is dollar and there is plus, so dollar and plus, so plus is having higher precedence, so plus will be pushed on top of stack. Again plus and id, so plus and id is having greater precedence. So again what will happen, we can uh, again push this id on top of stack. Now we will see the next one. We are having this multiplication sign and this id. Again for id and multiplication sign, if we see id is having greater precedence to that multiplication sign, that's why id will be popped out and plus will remain on top of stack. Now plus and then multiplication sign, again plus is having less precedence to that multiplication sign, so this multiplication sign will be pushed. Then again we will see multiplication and the id on top of input buffer, so id is having highest precedence, so id will be pushed. Again uh, so id and there is dollar, so id is always having higher precedence and dollar is always having lowest, so that id will be popped out. Similarly for multiplication and plus sign, and finally we will have dollar in both side, in top of stack and the string. So that is the condition when we say it as accept. So in this way the operator precedence parser works. Now there are some rules, there are something which can be used for this establishing precedence relationship. So For that, we construct two lists. First is the first stop plus, then last stop plus. So first stop plus is actually list of all terminals which can appear first of any right hand side of a production. Then last of is the last list of terminals which can appear last on any right hand side of production. So how we select it? For any production like this, we put this first non-terminal, then first terminal, then if there is non-terminal we push that non-terminal and the terminal after that non-terminal to the first stop, till we get the first terminal we put all the things on first stop. And similarly for last stop we write like the last terminal, and if there is last non-terminal then we will write that also, and then we also, and we use the closure. And after taking closure means we have to take each non-terminal in turn in order and look for the first stop list and add its own first symbol list to other which it occurs. So what we do, we take closure of the all the non-terminals, and then we will actually append this on the first stop list of the particular terminal, and then we will eliminate all the or we can say drop all the non-terminals from the list. We will see later. So like here ETF grammar, uh, later I can write it. So let me share the screen. So we are given this grammar: E derives E plus T, or T, then T provides T multiply F for F, then F provides E for ID. What we have to create? We have to create first stop plus of E, then for T, then for F, and similarly for then last stop plus. So let's get started. Uh, for first stop plus, we will first see the first stop of that non-terminal. So we will first calculate the first stop of E. Okay. So first of E will be equal to, if I use it, so from here first stop of E will containing this E, then this plus, then from we have got the terminal here, then we will go to the next production from E, we will get T. So first stop of E will be E plus and T. Similarly first top of T will get T, then multiply, then F. Now coming to the first top of F. So first non-terminal we have got is this open bracket. So we have got the first non-terminal, we will not go forward. Now coming to the next production, it is showing ID, F derives ID. So here, from here we have only ID. So we are done with the first top list. Now for the last top of E, what it will contain? For the last top, we will see the last terminal. Okay, so from this, what we have got? We have got T, and from this, what we will get? We will get this T, but T is non-terminal, so that will be there in the last top list. We have already taken with the help of the next production, and from here we will go to next one. We have got plus. So last top of we will having this T and plus. Last top of T will be having this F and multiplication symbol, and from here F again. So there will be no other symbol. Now coming to last top of F. So from this we have this close bracket, and from this we have this ID. Okay, so now we have this first top and last top list. Now we will go to first top plus and last top plus list. So first top plus list of E. What will be there? From first top plus list, we will take the closure of the symbols. Okay, so what we will get from first top list, we have got E plus T, E plus and T. Then we will go to T. We will go to T, and we will use the first top of T due to closure property. So we will take closure of E and T. First top of E will be first top of E, first top of T will be there. So from here what we will get, T is already there, we will have multiplication symbol and F. And first of now we have F, we should take first top of F also, so that will contain open bracket and ID. So this is the case. Now we have taken overall closure. Now we have to eliminate the non-terminals. From here we will get the final first of list, first of plus list, sorry. First of plus E will have plus multiplication this and ID. Now coming to the first top of T, first of plus of T, T multiply F, then closure of F, we will have open bracket, then ID, then again we will eliminate the we will drop the non-terminals, we will get multiply open bracket then ID, and first of plus list for this F, what we will get, we will again get open bracket and ID, both are terminals, so we will not take closure further. Now again for last stop plus, list for E, we have T, then plus, then for T we will go to last stop of T, so that is containing F, then multiplication symbol, this one, and for F we will take this close bracket and ID. Then we will eliminate the non-terminals. Last stop plus of E will having plus, multiply, close, ID. Stop plus of T. So this is the one. Then last stop plus T will having F star, and from F we will take closure of F, so we will take the list last stop list of F here. So last stop list of F is containing this close bracket and ID. So this is done. Now for last stop of F, what we will be getting, that is close and ID. So, and actually we forgot eliminating the non-terminals, so that is actually close then ID. So as you will see the PPT, we have got the same results here. So for first stop of E, first stop of E, first stop plus of T, first stop plus of E, then last stop, and last stop. Okay, so in this way we calculate the first stop plus and last stop plus list. Now coming to the next part, how we will actually take decision on precedence. So this was the case. Now we are given the this first stop plus and last stop plus list. What we will do, we will take these rules, constructing precedence matrix rules. For this, whenever terminal A immediately precedes non-terminal B in any production, put A less than alpha, where alpha is any terminal in the first stop plus list of B. So if there is a terminal A and there is a non-terminal B, and B is A is just after is just before B, then we will write A less than alpha if alpha is having first stop plus list of B, and if it is just after any non-terminal, then we will see the last stop list of that non-terminal, and we will provide higher precedence to that last stop list terminal. And if there is a sequence ABC or AC occurs, then we will put A is equal to C and add relations this and this for all terminals in last stop plus and first of plus in respectively of S. So here you can see for if we see this just for example, this plus that is actually preceding following this E and preceding this T. So what will happen uh, for this plus T, we will see the first of plus list of this T, and we will provide the higher precedence to plus than these list members. Okay, so we have plus, okay, and from plus 1 minute, sorry, for plus T is there, so we will provide higher precedence to this first of means symbols. Okay, so I'm again starting. If we are given this kind of situation, we have plus before this T, so any terminal before non-terminal, so we will go to that non-terminal which is after that terminal. Like here T is after this plus, we will go to first of list of plus first of plus list of T, and we will provide the higher precedence to the members those are in this list of first of plus T. Okay, so first of plus T is having this star, then open bracket, then ID. So plus where it will be we will provide higher precedence to this ID, this open bracket, and this multiplication. Okay, so first rule is followed. Then we can see that E is following this plus is following this E. Okay, so what will happen, we will see this last of list of this E, and we will provide higher precedence to these members. So plus, so we have plus and this plus, so we have provided higher precedence to plus. Then we have this multiplication sign. It is having higher precedence. Then we have this ID with having higher precedence, and we have this close bracket with the higher precedence. Okay, again so this is one thing. Now if there is any something like AB ABB, like there is non-terminal in between, so there will be equal, so we can see there is equal. Okay, so in this way we actually count this first stop and last stop. We actually means data. Okay, so till now I have covered some of uh, the things which are all the things I think which are covered in this uh, week PPT by sir. So let's have written something about it. So quickly I can cover it also. So in basic parser techniques, there are two type of parsers. What we have covered is just summary and what we will cover. Okay, so it is summary of both. So in top-down parser, so there are two type of parsers. First is the top-down, then there is bottom-up. In top-down parsing, we can do it with backtracking. That we say it as brute force method, and there is the top-down parser which without backtracking, which we say it as predictive parsing. So there are recursive descent and there is LL1 parser. Then there are bottom-up parsers. There are three things. First is shift reduce parsing, then there is operator precedence parsing. That is the only parser which can which is bottom up and take ambiguous grammar. And there are some LR parsers. In LR there are multiple. There are LR0, SLR1, LALR1 and then CLR1. Then some points about them. So if type of grammar is like this, and which parser will work. So for ambiguous grammar, no parser works, only this operator precedence parser works. Then there is unambiguous grammar, all parser works. For left recursive grammar, top-down parser doesn't work, but bottom-up parser works. Right recursive grammar, there is no problem for anyone. Non-deterministic grammar, the top-down parsers are not fruitful. Then for bottom-up, they can do. For deterministic grammar, all can. So some points. Um, Parser is a software or syntax analyzer. Top-down parser are of two types. First is this TDP with backtracking. We will try to go all possibilities, and if any possibilities goes wrong, we go back and choose next possibility. But without full backtracking, we will generate string exactly that is required. Then for bottom-up parsing, we have shift reduce parser. Shift means we will push on stack, and reduce means we will pop. Then we have operator precedence parser. We have LR parsers. We are scanning a string from left to right, and for R, reverse of rightmost derivation is used. That's why we write it as R. Then recursive descent, we are going to write recursive function for every production, and there are some non-recursive descent parser. And this is how top-down parser work and bottom-up parser works. So in suppose we are given this grammar and we are given this string. So what we can use, what production we can use, that is actually taken care by the parsers. So like here, from S we went to this A B E, then A will derive ABC, then B will derive D, then A will derive B. In this way, so mostly what we have done, leftmost derivation is generally used. So we first took this A, and from this A we derived ABC, then from this A we will derive B, and then leftmost is remained with B, so we will derive D from here. Then in case of rightmost, sorry, bottom up parser, we use the reverse of rightmost. So means reverse means we are reducing using rightmost one. So we are given this AABE from S. Now we will use the right symbol, B to D. We will so AADE. Then we will reduce this A non-terminal, ABC. Then we will reduce this A to B. So that actually happens. So those things we have already covered. First follow we have covered. For recursive descent parsing, if we are given some grammar like this, uh, we have to write recursive descent parser for it. Then for every non-terminal, we can write function like this. Uh, so if we are having L is look ahead, we can also write some simulation kind of machines. We can write this function also. So for every non-terminal, we will write match, and uh, for every sorry, for every terminal we will write match, and for every non-terminal we will just write function, and for every matching we will take get character. It is simply a C program. If we can use. Okay, so now coming to the next part, let's solve the questions of previous year. Then we will, if time will remain, we will try some other things. So uh, this is the question. uh, we are using shift reduce parsing, and for shift reduce parsing, we have given this grammar, and we have to provide uh, in shift reduce parsing the rule applied for the force reduction. So can you solve it? Okay, if you can solve, that will be far better. Just write the answers. I am providing 2 minutes for it. Just write, and this is also there in the PPT, so you can also use from there and take reference from there. So you can go to PPT number 10 for this. There is similar kind of example given in weak content. So the question is ID plus ID multiply ID. So what we will do, we will create, we'll use a stack, we will use a string and the action. for question 1. And top of the stack will be this id multiply id. So first what we will do, we will shift it so now we will shift this id to on top of a stack. We will remain with id and this. So the question is fourth reduction. Okay, so the rule we are given is e plus e or e multiply e or id. So we cannot reduce in first round because if we will reduce it, we will be there for this. It will accept it. Means that will be the acceptance condition. So we will again shift plus, then again id plus. Oh, sorry, I'm not mentioning it. Okay. So id we can reduce it to e. So e. Now we will shift. So shift will provide me plus on top of stack. We will remain with id, then id. Now again we will shift e plus id star id dollar. So now we have id, we can reduce it. We are having e plus e id, then this. Then again we can shift then again shift. then we will reduce it. E derives id, so there will be e plus e into e. Now we will reduce into e derives e, sorry, e derives e into e. So that will reduce it to e plus e and dollar. So actually we are taking rightmost derivation, that's why we are using it. So our fourth reduces here for e derives e into e. Okay, so fourth one is B. Answer is B. Now coming to the next one. A bottom-up parser generates, it is very simple answer, the rightmost derivation in reverse. It is from theory. In shift reduce parser, parsing and accept in shift reduce parsing and accepted input string reduces to the start symbol, then there is an optimizer compiler is optimized to occupy less space, and optimize the code. C is optimize the code, and D none of the mentioned. So for this, the answer is D. Why? Because the optimizing compiler program is actually that used to minimize or maximize specific characteristic of executable program. Okay, so optimizer compiler, what it does, used to minimize or maximize specific characteristics of an executable program. Okay, next one is for this rule, what is the first stop of T? So for first stop of T, uh, we will see the first terminal. So that is actually XYYS. From here we can see X is there. From here we have Y. So XY will be there in the list. The answer shown is B, but there should be XY. So I'm discarding it. I will, from my side it should be XY, but I will recheck and retry it in next class maybe. Then there is, by considering the rule, B derives TQQS, which of the precedence relation between T, Q can be inferred? So for this, very simple uh, third rule. If there is A, B, B or A, B, there will be a simple rule will be given. The precedence will be same. So here there is TQ and QQ. So TQ and QQ will having same precedence. Answer is A. So that is all from previous year questions. Now we will do some of the questions just for understanding. So for example, if we are given some grammar like so we are done with the week 5 content according to this question answers and the PPT. So I am adding some other questions. Let's try it. So we are given a grammar. S derives A or A, then A derives A. We have to use LL1. We have to see whether it is feasible or not. So grammar is actually ambiguous, I think. But if we check using the overall method of LL1, then what we will get? Let's see. So first we will have to calculate first and follow. First of this and follow of this, we have two non-terminals A. So first of S will contain this A, and from A we will go to A only, and first of A will also be A. Follow of S will be dollar, and follow of A will be follow of S, that will also be dollar. So both are same. Now coming to the parsing table, we have two non-terminals S and A, and two terminals A and star. So when we will be at this what we say S, and we will see from S where we can go. So we have only one first, and there is no other symbol for first, and there is no epsilon. So what we will get? We will get S derives A and S derives capital A, both in this column, both in this cell. And for A we have A derives A. So from here we can say it is not feasible for LL1, because whenever LL1 parser will go here, it will see that we have two productions. It will check for which production to follow, and it will get two answers. That's why it will not work. Now there are no much questions about it, about the topic covered. So let's solve some of the one question of VTF grammar using um, this LL1 parsing and then recursive descent by our own. So the grammar is E derives E multiply T, T, T derives T divide modulo F or F, and F derive E or ID. It is similar to that question what we have solved, but there are some different signs. So let's solve it using LL1 first. What we have to do, we have to just take the first and follow. Sorry, just a second. So what we do first, we have to first check for this left recursion which is there. uh, just a second, I think my device battery is low. Let me connect to the charger. Okay. So as you can see from here, it is actually left recursive. So first we have to remove the left recursion. So what we will do, we will write it like E derives T E dash, then E dash derives multiplication T E dash or epsilon, then T derives F T dash, then T dash derives modulo F T dash or epsilon, then F derives P or ID. That is the non-left recursive grammar. Now we can check it. We can now use this grammar for calculation of our this first and follow. So we have five symbols: E, E dash, T, T dash, F. What will be the first of this E? So first of E will be first of T, first of T will be first of F, first of F will be first of F, that is this open bracket, and ID. Now, first of E dash is containing this. First of E dash is containing this one and this epsilon. So star and epsilon. And for first of T dash, we have this modulo and epsilon. Now for follow. For follow, we have follow of E. Follow of E will always contain dollar, and from here we can see follow of is close bracket. Then follow of E dash is actually follow of E dash, follow of E, that is dollar and close bracket. Then follow of T. Follow of T is the first of E dash. So first of E dash is having this symbol, then there is empty string, and from empty string we will what we can infer from follow of T will be follow of E dash, then follow of E dash will be follow of E. So it will contain follow of E also. Similarly for T dash, follow of T dash is actually follow of T from here and from here. Now coming to the last one, follow of F. Follow of F will contain what from here it is first of T dash. So first of T dash is modulo, then there is epsilon, so epsilon will be the empty string. So from here we will learn to follow of T dash, and that is multiply dollar and close. So we have calculated the first and follow. Now we next step is to we have you have to create this parsing table. So parsing table for the previous one, what we have, so we have ID, we have multiply, we have modulo, open and close brackets, and then dollar. You have E dash, T, T dash, F. So E on ID, we go to first and follow. So we have E and ID. So we will write the production here. So we will see first of this E, we have ID and this open bracket. So we will write the production of E on ID. E derives T dash and E derives T dash. Similarly for T and F also we have same one. So for T derives FT dash, T derives FT dash, F derives where we can get ID from ID, and for open bracket which first will follow will be means responsible this one. So for this we will use this production. So F derives E. So these three are done. Now coming to E dash. So first of E dash, if we see, it is containing this multiply and this epsilon. So multiply can be provided with the help of this, and epsilon can be provided with the this production. So multiply E dash derives multiply T E dash, and then uh, if there is epsilon, we have to go to the follow of E dash also. So in follow we have these two, and these two will come when there will be epsilon in the production. So what we have got, E dash derives epsilon, E dash derives epsilon. Now coming to the T dash, from T dash, what we can infer, we have modulo, then epsilon. Epsilon will take us to these three. So modulo ft dash derives epsilon. Just a second. So there is, so this is the parsing table. Now if we are provided some string like kind of id multiply id modulo id, so how we will parse it? It is very similar to the example given in PPT, just symbols are different. It's just for practicing purpose, nothing else. So we will append a dollar after it. Now what we will create, we should have three things. We should have a stack, we should have input, we should have action or remarks. So on a stack we will have the start symbol E. On input we should have the string, and on action what we will do, we will go for the action based upon the input and the top of stack. So top of stack is E, and input here is this. So top of stack is E and input is ID. So what will happen, we will go to use this one. Okay, so we will do parse E derives T dash. Okay, now how we will push it, the leftmost symbol will be on top. Okay, so E dash T, then there is ID, 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 dollar. Now we have T on top of stack. We have T and this ID. Go to the previous one. We have this T. We have this ID. What we will get? We will get this one. Okay. So what we will do? We will just write parse T derives ft dash. So about that T and just push this ft dash. So e dash ft dash. Now we have id 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 dollar f and then id. So what we get? F derives id. So id and f parse f derives id. Okay. So e dash t dash id 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 dollar. So now we have id, this id. So what we will do? We will advance input. So it will be passed, it will be popped out, and we will remain with t dash and the rest of string. Now the pointer will be on this one. So what we will do? We have this t dash and this multiply. T dash on multiply, it provides t dash derives epsilon. Just go to it. Parse t dash derives epsilon. So we are now at this id id dollar. Now e dash and this one, we will get this. So e dash derives parse e dash derives t dash. Sorry. So we will pop out this e dash and push this e dash t id id and this. What we will do? We have this one. We can advance input. So this input is red. Now our pointer will be at here and it will be popped out. So what we will have? Just write e dash t id modulo id dollar. Now go to t and id. What we will get from t and id? We have t derives ft dash. Parse t derives ft dash. So just pop out it e dash t dash f id. So id and f, we know we have to parse using f derives id t dash id 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 dollar. So this one we have to advance input. Now we will have at e dash t dash multiply id dollar. So now we have t dash and modulo. So go to t dash and modulo we have t dash modulo f t dash. So parse t dash derives modulo f t dash. So e dash t dash f modulo, we have this we can advance input. So we have to parse again f derives id. So e dash t dash id dollar a, and from here we can again advance input. Now what we have this dollar and e dash t dash. So what we will do, just go to the table, we have dollar, then t dash, we have t dash derives epsilon. So parse t dash derives epsilon, we will remain with the, this is pop out dollar. Now e dash and epsilon, e dash and dollar, sorry, so e dash derives epsilon. So parse e dash derives, sorry, epsilon. So e dash derives epsilon. So there is nothing, there is dollar, and this is the symbol where we say it is done. So this string is valid for this LL1 parser, and it is parsed using LL1 parsing. In this way, we can parse the strings using LL1 parser. So this is one example, and there is one small example for uh, convert grammar to operator precedence grammar. So this is, we are given e derives EAE, or this, or minus e, or id, and a is plus or minus or multiply or division or this. So it is clearly not a operator precedence grammar. So what we have to do, we have to put these derivations to this grammar. So we will put this a values to this a value. So it's very simple. What we will get, e plus e, e minus e, e multiply e, e divide e, e to the power e, then within bracket e, then minus e, then id. So this is the way to convert operator precedence grammar. Very simple one. Then if we take a question, just to raise a term constructing for operator precedence only. This is also given in the lecture. So I will not go with the first stop and other things. We are given this string, although it is ambiguous grammar, but in previous lecture I have taken this example. So what we have to do, we have to actually parse it using operator precedence parser. And we are given this table. So the table is like, now this is this. Okay, so this is the table given, and based upon this we have to parse this string. So what we do, we first generate the we first write the string with the precedence. So what it will contain, we will just write this a little distant. Okay, next page. So we are given this, we should have this dollar starting and end of the string. Okay, so dollar is from this table is having less precedence to this, then A is having greater precedence, then this A is having always greater precedence, and then dollar. So what we will do, we can go in this way, like we will search for first uh, this greater symbol, and then for next lesser symbol, and based upon that we will parse it. So from here we will see sorry, so we are going with greater symbol, we got this, and from left to right we will go to the less symbol. So this first less symbol is this. So we have got our first token, what we have to reduce. So from here what we got, we have got this A. So the uh, production what we can use is S derives A. So what we have got here, we have got this S. Now there is this. Now in next step what will happen, uh, you will again search for the uh, greater symbol. So this is there, this is there, and this is there. From left hand side This is for other greater symbol. From left hand side we will get the last less symbol like this. So we have got this one. Now from here what we will get? S, again the same production, S, likewise. So again we will come to this one. Similarly, we are following the same algorithm what is written in the PPT. So S, comma S, then this. As we parse or reduce to the production, then we will remove that greater or less symbol. Now here what we have got this one. Now which production we can use? We can use from here S derives L, again from ls we can move to L. Now from this what we can get? This is actually this one. Again S, comma S, then again this one. Again, okay, so remained it. Say example 2. We have pages later. So remained example 2 is here. What we have got? We have got this one. Okay. So we are at this greater S, comma S, S. Now we will again reduce it. Then again this can reduce to S, and S is the initial symbol, so it will be reduced to the final state. So we have got this, so this is the parsing is done. So in this way any operator precedence parser works. So today we have covered something like for LL1, then from LL1 we covered how to create first there should be non-recursive grammar. Then from non-recursion we will create the parsing table. Then there will be stack and input buffer, and based upon that parsing table we will take our decision. That is the LL1. And for operator precedence, what we will do? We will use that first stop and last stop, first stop plus last stop plus. From there we can get precedence, we can create table, and based on that table we will search for this and this, and for there if we will land to double dollar we will say the parsing is done. So in this way all the parser what we have covered today will work. Okay, So that's all from my side today. सर ऑपरेटर प्रेसिडेंस में प्रेसिडेंस कैसे डिसाइड होती है? ओके, ऑपरेटर प्रेसिडेंस में प्रेसिडेंस के लिए फर्स्ट स्टॉप एंड लास्ट स्टॉप का यूज़ किया जाता है। और नेक्स्ट थिंग, अगर प्रेसिडेंस सेम है तो उसकी एसोसिएटिविटी ली जाती है। ओके, तो लाइक अगर हमारे पास सेम प्रेसिडेंस के, मान लो हमारे पास प्लस प्लस है, देन अगर प्लस को राइट एसोसिएटिव कहेंगे तो हमारा राइट वाला जो प्लस होगा उसकी प्रेसिडेंस ज़्यादा होगी। ओके, और बाकी जो प्रेसिडेंस है वो बेस्ड अपॉन तुम्हारा फर्स्ट ऑफ प्लस एंड लास्ट ऑफ प्लस लिस्ट निकलेगा। ओके, एनी अदर कंफ्यूजन? Yes, videos of all seasons, last 4 seasons are uploaded. Today's video I will upload within 2 or 3 hours, based upon how much it takes for uploadation. Okay, so link is there in course menu. If you go to course, you will there is a separate section after this week. There are week columns, and after that week cell there is problem solving season. So just click on there, you will get the Excel sheet of all the things. Okay, so thank you all for joining this. We will meet next week with the problem solving session of week 6. Okay. Yes, yes, yes. ये वीडियोस आपको कोर्स पेज पर इसका लिंक मिल जाएगा। GC, अगर आप कोर्स पेज पर जाओगे, कोर्स पेज पर आपके पास okay, so thank you all.